I'll be the first to admit that I am an astronomy nut. I have loved looking up the stars ever since I was a child, and this interest has continued well into my middle age. I'm the proud owner of 2 telescopes and probably many more before I die, and I've taken plenty of images that others may consider poor but are pretty much my pride and joy from my astronomy. Today I'd like to take you on a journey from the Earth to the stars and beyond. In the early 1600s, Galileo Galilei began turning his telescopes from the ground towards the heavens. On 7 January 1610, Galileo pointed his telescope towards one of the moving stars, Jupiter, and he described 3 fixed stars, totally invisible by their smallness. He further noted that they were all extremely close to Jupiter and in a straight line through the center point of the planet. Over the following days, Galileo noted that these stars moved in relation to Jupiter in a way that was completely contrary to the known laws that dictated the motion of the other stars and planets in the sky. 3 days later, he noted that one of the stars disappeared behind the planet. Galileo concluded these newly identified stars were actually moons orbiting Jupiter, and he became the first human to observe an object that was captured inside the gravity well of another celestial object. Time for a quick little personal story. Not long after I bought my larger of the 2 telescopes, the 16-inch truss Dob, I was out in my yard and I was looking at the stars and I pointed it at Jupiter. And when I looked at it, I'd never seen it with that magnification before and that bright of light. And it didn't quite look right to me. There was a small spot on it and there was a small bright spot on it. And I didn't understand what they were. I observed these 2 anomalies for several hours and they did appear to move to me. And this is the first time that I'd observed Jupiter. So I downloaded an app that allowed me to look at Jupiter and its moons. And as it turned out, I was watching the transit of Io and a shadow of Europa crossing the surface of Jupiter. And I witnessed it firsthand in real time. Well, over the coming months, Galileo intently observed these objects, identifying a 4th moon and studying their orbital periods and predicting their transits and occultations. Io, the innermost moon, became of some interest to Galileo due to its extremely short orbit and extreme predictability. He also noted that the moon didn't just disappear when it went behind the planet, but it also happened before and after the planet occulted it. Whether it was before or after was all based on where the Earth was at in relation to Jupiter's orbit. Galileo surmised that the shadow of Jupiter, as it was cast out in the opposite direction away from the sun, was falling upon Io, causing it to go dark before the planet actually blocked it from our view. And this image, later created by Ole Romer, shows a bird's eye view of the orbital dynamics of the Earth and Io as it goes around Jupiter. Knowing that the Earth's orbit is actually faster than the distant Jupiter, you can see we are constantly playing a game of catch-up or runaway from this giant planet. And with an anti-clockwise orbit, you can see at positions F and G, we will see Io entering the shadow of Jupiter. But while at positions L and K, we see it emerge from the darkness. During opposition, we will not see it affected by the shadow, but only the blockage of Jupiter itself. Over the next 5 years, Galileo was able to exactly time the orbit of Jupiter, down to a fraction of a second. This orbit was 42 hours, 28 minutes, 31 and 1/4 second. And with this prediction, he was able to say exactly to the second that Io would disappear or emerge from the shadow or be blocked by Jupiter itself. Galileo was so confident in his predictions that he proposed it be used as a universal clock across the planet and even on ships. The Spanish crown actually created a prize for anyone that could design a clock capable of going to the rough seas on a ship that would allow the crew to identify the exact time at Greenwich Mean, thereby finding how far away they were and knowing their longitude. While it did not prove practical for a captain to find the time of the emergence of Io, it did show how exact the timing of the orbit was. Now let's fast forward to the 1670s, and we go back to the Danish astronomer Ole Romer. Romer continued the observations of Jupiter and further exacted the time of Io's orbit. Romer did, however, note one oddity. While the transit or occultation time was exact, and could be repeated day after day, if you observe 4 months prior or after Jupiter's opposition, the timing was still exact, but it had shifted 7 minutes. Put simply, If at opposition you calculated the times and extrapolated it out 4 months and predicted when it should occur, and this time, let's say it would be midnight, the time would actually occur
at 12:07.
But the interval was still at 42.5 hours. And during this time, from opposition to K, as you measure the orbits, you can see it slowly drift from that prediction until it's at that 7-minute late point. Now, if you measure it again in 4 months at point F, after the time when Jupiter is actually obscured by the sun, the eclipses are 7 minutes late. Then they slowly drift back to the expected time when you're back at opposition. What could have caused this delay? How could the timing be so precise but off? Up until this point in history, most scientists and scholars had believed that the speed of light was infinite and instantaneous. On the human scale, that was clearly the case for everyday observations. Romer, however, had just discovered that by Earth physically moving farther away from Jupiter, and on an astronomical scale, the speed of light could be observed and calculated. The time it takes light to travel across the orbit of the Earth is 16 minutes and 14 seconds. And this is what Romer observed. While the Earth is farther away from Jupiter, it literally takes light longer, but the day-to-day observations are still the same. And as we're closer, the light takes less time to reach us, and the day-to-day observations are the same. The orbit of Io never changed. The only thing that changed was how long it took the light to get to us. Now, my question is, how are these observations possible on a flat and motionless Earth? To me, this is proof that Jupiter is physically moving farther away from the Earth. You could argue that Jupiter is moving and not the Earth, and that's what Ptolemy tried to do 2,000 years BCE. He tried to explain how all of the stars wandered in the sky independent of each other on their own epicycles, but as you can see in this image, it just doesn't work that way. So our only options for belief are A, every object in the sky wanders on its own as predicted by Ptolemy, a belief that has been thrown out for thousands of years. B, all of the objects in the sky are projections or holograms on the firmament, or they just appear to be observing the laws of physics, such as orbital dynamics and the speed of light. Or C, the sun is actually the center of our solar system, and everything does move around it. I don't know, what do you think?
I'm just your average person with a base level education, but a passion for science. These videos are based on my perspective of the real world, so if I'm wrong, please tell me. But don't just comment, "You're wrong." Tell me where I'm wrong, and let's start a dialogue on what I got that's not correct. I'm always open to other interpretations of what I'm seeing, but just stating "you're wrong" tells me you don't have a basis for your argument. And I'm a firm believer that extraordinary claims require extraordinary evidence. Thanks for making it this far. If you like my videos and the information I provide, a subscribe and like is always appreciated.
And until next week, stay flat.